Hi guys, welcome back to my YouTube channel. My name is Dhanushar. I am studying in Venkatesh College of Engineering. Today our subject is mathematics for CSE stream. In that our topic is vector calculus. Vector calculus. Introduction to vector calculus. Vector calculus is a powerful mathematical discipline that extends and concepts of single variable calculus to multi-dimensional spaces. It provides tools for analyzing and understanding the behavior of vector fields, which are crucial in fields like physics, engineering, and computer graphics. Vector diagram. Vectors and vector operations. Vectors are mathematical objects that have both magnitude and direction. They are commonly represented by arrows in 2D or 3D space. Basic vector operations includes addition, subtraction, scale, multiplication, and finding the dot product and cross product of two vectors. Vectors can be used to model physical quantities like force, velocity, and acceleration, allowing for powerful mathematical analysis of these concepts. Scalar and vector fields. Scalar fields assigns a single value to each point in space, such as temperature or pressure. Vector field assigns a vector or direction and magnitude to each point, such as wind velocity or electric fields. Scalar fields are represented by a single number, while vector fields have both magnitude and direction. Understanding the differences between these two types of fields is crucial in vector calculus. Gradient of a scalar field. The gradient of a scalar field is a vector field that represents the direction and rate of change of the scalar field at a given point. It points in the direction of the maximum rate of increasing of the scalar field, and its magnitude is equal to the maximum rate of change. Calculating the gradient involves taking the partial derivatives of a scalar field with respect to each spatial coordinate. The gradient vectors can be used to find the direction of maximum change and to compute line integrals and surface integrals. Definition. The curl of a vector field measures the local rotation of the field around a point. It is a vector quantity that describes the spinning moment of the field. Calculation. To calculate the curl, you take the partial derivatives of the vector field components and combine them in a specific way. This reveals the rotational behavior of the field. Physical interruption. Curl is important in fluid dynamics, electromagnetism, and other areas where rotation is a key phenomenon. It can describe things like vorticity in fluids or magnetic fields around a current carrying wire. It's all about the curl of a vector field. Line integrals. In this, firstly, a line integral is a way to calculate the cumulative effect of a vector field along a specific path. It is used to measure quantities such as work, flux, and circulation within a vector field. Line integrals are powerful mathematical tools with applications in physics, engineering, and beyond. They allow us to quantify the behavior of vector fields in a precise and meaningful way. Surface integrals. Definition. A surface integral calculates the flux or flow of a vector field over a surface in 3D space. Applications. Their applications are used to compute properties like work, charge, mass, or energy flux passing through a surface. And the calculation involves the integration the dot product of the vector and the cross product of the vector over the surface area. Green's theorem, fundamental theorem of a line integral. Green's theorem establishes the relationship between a line integral around a closed curve and a double integral over the region enclosed by that curve. Connecting integrals. It allows us to convert a difficult line integral evolution into a more manageable double integral in the plane, making calculations simpler. Applications in physics. Green's theorem has important applications in physics, such as in the calculation of work done by a phasing force field and the flux of a vector field through a surface. Conditions for application. Green's theorem can be applied when the vector field satisfies certain continuity or differentiability conditions and the region is simply connected. Applications of vector calculus. Electromagnetics. Vector calculus is essential for modeling electric and magnetic fields, which is crucial in design of electrical circuits, antennas, and other electromagnetic devices. Fluid mechanics. The concept of gradient, divergence, and the curl are used to analyze fluid flow and pressure, enabling the study of aerodynamics, hydrodynamics, and the behavior of liquids and gases. Quantum mechanics. Vector fields and their derivatives are fundamental in describing the behavior of subatomic particles and the evolution of quantum states, providing a mathematical framework for quantum theory. General relativity. Vector calculus is employed in Einstein's theory of general relativity, which models the curvature of spacetime and the motion of the objects under the fluency of gravity.